Okay, all right, guys. So this is just another video to complement the first one that you had in there. On here, I'm gonna go over some of these web assign. Some, not all of them, because you have to do them, right? Um, for example, some problems you are given mass volumes of water, and you have to find how much energy or how long or the final temperature. It depends, right? So here it says Lake Ontario has that amount of water. So they give you the volume of the lake. And you're going to assume that the water density is normal density of water, which is 1,000 kilograms per meter cube. How much energy in joules you need to raise a temperature from 16.4 to 20.8. You're going to see how much energy you need to raise by basically 4 degrees Celsius, which, I mean, it's a lot. And when you think about climate change or global warming, right, it makes sense why some scientists, not all of them, but some are a bit concerned about the temperature of the oceans rising by 1.5 degrees. You may think it's not a lot, but when you look at the amount of energy, you will realize that, okay, well, have to be a bit concerned, maybe. So in question 1, if you have that volume of water, 1.6 times 10 to the 12, right? That's meter cube. The density of water, I'm gonna label it R. Let's stop sharing my screen. See, I did something here. There. The density of water is 1,000 kilograms per meter cube. So the mass of water is density times volume. Basically, 1.60 times 10 to the power of 15. That's 10 to the 3, 10 to the 12 when you multiply, and this is in kilograms. So the energy is basically heat, Q, equals to M little c delta T. So the mass is this. So you see that's a lot. Then you multiply by the specific heat capacity, which is 4,186 joules per kilogram Celsius. Leave it like that because this is already in kilograms, so kilograms will cancel, and then Celsius will cancel with a change of temperature, which in your problem is 20.8 minus 16.4. That's 4.4 Celsius. So that's the energy in joules, right? So if I use a calculator for this, 1.6 times, I calculate 1.6 times 4,186 times 4.4, I get 469 times 10 to the 15 joules. That's basically 4. I can say 2.95 times 10 to the 1, 2, 3, 4. I divide by 10,000, 10 to the 19 joules. That's a lot of energy, right? A billion is 10 to the 9. So this is a billion. More than that, right? The amount of joules. Now in calories, you will divide this by 4.18. Still, it's going to be a lot. So that's why that's a concern, because you need a huge amount of energy for that to happen. Even if it was just 1.5 degrees, it will be a lot, right? Just for the lake, imagine for the oceans. How many years will it take to supply this amount of energy using power of 1,400 megawatts generated by a power plant? Let me show you that here. So they're giving you a power plant, right? So let's do it here. This is part A. Part B, if the power is 1400 megawatts, that's 1400 times 10 to the 6 watts. Okay? That's energy, that's power. The relationship between energy and power is energy is power times delta lowercase t. That's time. Now, energy is this, power is this, so I have to divide. But the time will be in seconds. So my delta little t will be that divided by this. Okay, since you guys have this a recording, right? You guys can like take a snapshot, I guess, when I raise this. So my delta t, the time in seconds, is that division. So let's see what I get. So 2.95 over 14. Oh, you know what? Let's do 2.95 over 14. I get 0.21. So 0.21 times 10 to the 10, 19 minus 8 is 11 seconds, which is basically 2.1 multiplied by 10 divided times 10 to the 10 seconds. But the question is in years. So you want to find this in years, delta t in years, you're going to divide 2.1 times 10 to the 10 by 365 days, 24 hours, 3,600 seconds per hour. So you just do 2.1 divide by 365 divide by 24 divide by 1,600 times 123, 123, 123. So 665.9, basically 6666 years. How about that? More than 6 centuries. Makes sense. All right. There you have it. That's a nice problem. I think the concept, right? You have to be careful with the units. Of course, you see how I changed seconds to hours, to years. Everything was given in the metric system, so you don't have to worry about that. Okay. So that's basically how, oh, sorry, here. That's the procedure for part B, right? Again, power times time is energy. So energy over power is time, but that's time in seconds. You have to change seconds to years. So you divide the amount of seconds and the conversion, right? 365 days, 24 hours, 3,600 seconds. That's the amount of years, all right? There you have it. What else we have here? Let's see. Let's do a latent heat. Yeah, this one is good. Problem 6. So in the first video, you saw a lot of problems with, Q equals to MCT and all that. So problem 6 is, suppose 9.50 times 10 to the 5 joules of energy are transferred to 2.42 kilograms of ice solid at 0 degrees. The latent heat of fusion and the specific heat of water are those values respectively. Calculate the energy to melt all the ice into liquid. Okay, let's see. So that's the nice problem. So we're doing phase change there, right? So for the phase change, you will do This is problem 6. Latent heat, QL, equals to MLF in this case. Latent heat of fusion. Mass times the latent heat of fusion, right? Which is 3.33 times 10 to the 5. So the energy to melt the ice is just, for part A, you just multiply 2.42 kilograms times the latent heat of fusion times 3.33 times 10 to the 5. Joules per kilogram, so you will get in joules. So that's 2.42 times 3.33, 8.05 times 10 to the 5 joules. That's the energy to melt all that ice. But then they ask you how much energy remains to raise the temperature. So once you melt the ice, you're gonna increase the temperature of water. And yes, you have an excess of energy because the input, so the energy given, let's put it like that, is 9.5, right? 9.5 or 9.50 times 10 to the 5 joules. So we're gonna subtract. For part B, you do this minus that. And look, 10 to the 5, 10 to the 5, so I can just do 9.50 minus 8.05, which is 45, 50. So the energy left, 1.50, 1.45 times 10 to the 5 joules, right? Yeah, that's the end. That's this minus that. So that's the energy that you can use to increase the temperature of the water now that is liquid. So that energy left, you make it equal to mc delta T. So what's the question asking you? Oh, the final temperature of the liquid. All right. So let's write this. For part C, this energy is equal to the mass. The mass doesn't change. It's conservation of mass, right? 2.42 times the specific heat of water now, because it's water, liquid now, times that delta T. Let's put delta capital T. So let's find delta T. Delta T is that divided by that. So 1.45, oh caramba, 1.45 times 1,232 divided by 2.42 divided by 4186, 14.3 degrees Celsius. That's the current temperature. Now, what's that? Oh, the final temperature of water will be T final minus T initial. T initial is 0 degrees Celsius. What do you think? This is the final temperature, right? 14.3 degrees Celsius. Not bad. Another interesting problem there. All right, let's do number 7. I want to show it to you so you guys can see it there, right? That's pretty clear. Let's see what else we have here. Let me share this with you. A 107 gram cube of ice at 0 degrees Celsius is dropped into 1 kilogram of water at 85 degrees Celsius. What's the final temperature of water? Okay, this is a nice problem because we're doing equilibrium. So you have 107 grams. So remember, guys, you want to convert those grams into kilograms, right? So let's draw the picture here. You have 1 kilogram of water and you have ice that you want to drop. This at 0 degrees Celsius and the water was at 85 degrees Celsius. And this is 107 grams. What's the final temperature once the ice has melted? All right. So the way I think it's better to do this is you draw a line like this. And you have 0 degrees Celsius. I'm going to draw this. I'm going to show you what that means. And this is 85 degrees Celsius. So the equilibrium is probably going to be around here. T. Water is going to drop the temperature. Ice, of course, is going to melt. And then it's going to increase its temperature. This melting is what you have to be careful. The ice is in solid state. So you have to melt the ice first, right? So you need to add the heat lost by the water is equal to the heat gained by the ice, right? Now, the heat gained by the ice includes the melting, the latent heat. So we just did that. QLF for ice is M of ice times LF. That LF is in the previous problem. So I will do, and then you have to add the heat gain by raising the temperature. That's just M of ice. Little c change of temperature. T minus 0. For the Q lost by water, Q loss is the 1 kilogram of water times the specific heat capacity of water times 85 minus T. You're going from 85 to T. For this will be, well, let's do here the Q gain. So this will be 107 divided by 1,000 in kilograms multiplied by 3.33 10 to the 5. You're going to add M C delta T, T minus 0. There you are. All this is equal to this. So let's do it here. That's how you want to reason. That's how you want to think. Q gain equals to Q loss. Q loss includes the melting down. All right. So let's do some of the math here first. Let's calculate the number here. Divide. All this is this. $448. 448 capital T that if I distribute here, right? This is just one, this.
Here, workshop, please take your center now. Buenas tardes a los padres y los maestros que están aquí para
That will give me 4, 6, 3,
por favor, ir a la librería.
as positive. And this, let's see. So I get 3,000 of 322,210 when I do this minus 6. So this goes to this side. So anyway. So divided by 4,634 by 4,634, my temperature will be what that? 69.5 degrees Celsius. You're probably wondering why that happens. That's because you are dealing with ice melting and water. They both have the same specific heat capacities. When we did a problem with the aluminum in the previous video, the aluminum has a very low specific heat capacity. So it raises or it changes its temperature easier, more easily than water. But here we're dealing basically with water and ice. So you will see a bigger change. So that's a nice problem there. All right. See, that's basically what I wanted to go over with this. There is the last problem, they give you like a calorimeter experiment. Just make sure that you pay attention at the data they give you. For the conductivity problems, remember that you want to use the equation K area, right, times T divided by length. When they ask you for the rate of energy, that's Q over T. So you just have to worry about K area and the length. All right, so maybe I can show you quickly one of the conductivity problems. So it's telling you that you have a window pane 0.62 centimeters thick with the dimensions to find the area. And the temperature outside, indoor is 23, outside is 0 degrees. What's the rate of transfer of energy, right? That's basically Q over T. The rate of energy transfer is power, basically. All right? So you are going to use the conductivity equation. So we finished with this already, right? So for the conductivity, Q over lowercase t, P, K area, delta T over the length. All right? You only need to figure it out at K. Now, for a window pane, a glass, if it's glass, K is 0.8. That is 0.8 for glass. The window has these dimensions. So right here, the window has dimensions. It says here 1.3 times 2.2. That's the area of the window. That was here. What's that change on temperature? Indoor is 23, outdoor is 0. So 23 minus 0 divided by the length. That's the thickness of the window. 0.62 centimeters. 0.0062 meters. You got to change that in meters. And we can find the rate of change. All right, let's find this. 0.8 times 1.3 times 2.2 times 23 divided by 0.0062. I get 8,487. So about 8,490 joules per kilograms, basically watts. And if you want to find the amount of energy lost per day, you will do the amount of power times the amount of seconds in a day. So remember, we just did that, right? You multiply 24 hours times 3,600. That will give you a number of seconds. You multiply by that, and you get a number of energy lost per day by this conductivity, all right? So that's basically chapter 11 homework, all right? I will do office hours, as you know. So if you have any questions, please let me know by then. See you later.